Oh, okay.
Yazuka.
That's a good one.
So you, YA.
Why, maybe, okay, YA is the most common.
Yeah.
So in my phone, it was red.
That was so funny.
And I was like, I don't know why my phone was.
But it was just that my phone was perfect. And then I realized that one day and then I like typed it back. I was like, you were so yeah. But now I know.
Okay, that should do it.
Did you ever talk about?
Oh, the last
I
thing.
just remember you.
But like I usually ask
Wait, is that what you said? Like fast.
or like the zoo
zoo?
is the same. So
Yeah.
Jack, can you give me a thumbs up if you can hear me? Awesome, thank you so much.
I'm not sure if this is still like Jessica.
I usually.
Okay, so here we go. So today we're going to talk surface chemistry. I wanted to revisit some of the stuff we did last time, just to make sure we've covered a lot of material. So, transition probability, it can be calculated or estimated using Fermi's golden rule. Fermi's golden rule basically says that there's a coupling of the initial and the final states. And then there's a number of starting and final states. And transition probability is just the sum over each of those possible initial and final states gives you the absorption. And the coupling is a product of a couple of things. The overlap between those initial and final states. So we talked about the electron hole overlap. The greater the overlap, the higher the probability. And then there are things like symmetry and dipole transition strength to worry about. This overlap thing is a big deal in quantum dots because it's one of the reasons why, it's one of the things that really strongly affects their properties. You change the size of the particle, you get very different transition probabilities. You can see, for example, in the strength of the first excitonic feature in these spectra, as you go from large dots and low energy to small dots and higher energy, the strength of the absorption increases. The same amount of cadmium selenide in each one of these spectra. I know that because they overlap, they're at the same value of absorption at high energies. And high energy absorbance is not size dependent, it's proportional to the volume of stuff. So you have the same amount of cadmium selenide in all of these spectra, and you can see this first transition is more intense than it is here. And that's a result of orbital overlap going up. So the strength of the transition is also related to the rate of that transition. Stronger transitions are faster. Quantum dots have these multi-charged species in them called biexcitons and trions. And the rate of their recombination, you can estimate just from the relative rate of the single exciton and counting the number of pathways available, right? And so these are examples of Auger recombination rather than radiative recombination. But this Auger recombination, as we talked about, is very important to properties. You've got a couple of different ways. There's two different holes here that this electron can recombine with. That means that that process is 2 times faster than the radiative transition, as we talked about. And you can count the number of trion pathways when considering how a biexciton might recombine. So I'm not going to go through the arguments again, but the important issue or the thing to remember is that the probability is related to the number of transitions in a multi-electron transitions. have more options. This gives rise to really complicated photophysics for quantum dots because quantum dots can become charged and uncharged with time, and you get these blinking traces. So up here at the top is the radiative rate for just a single exciton, but when you make trions, those trions have different radiative probabilities because Auger recombination turns on for those species. So the Auger outcompetes the monoexciton recombination and makes these states of the quantum dot darker. You can actually pull out the radiative rates for each one of those different processes from these traces, and you can see the radiative rate of the biexciton is much, much shorter. It's faster than these other rates. Now, this is a little complicated because what you're looking at here is luminescence intensity, but in fact, these species are not very luminescent, okay? So the lifetime is a product of the fact that these things decay very quickly by non-radiative pathways, okay? So the radiative, what you're seeing here is sort of what's left over and not consumed by non-radiative Auger recombination. All right, so in any case, blinking makes quantum dots sort of, I would say it's the biggest weakness of that material system, and it's a product of this complex charging behavior. We introduced the idea that quite a bit of this seems to come from surface chemistry, and so today we're going to talk about surface chemistry and relate that to some degree to the luminescence characteristics. So we've seen this sort of a diagram before, valence band and conduction band. Because this is a salt, you tend to describe this thing as being selenium-like. It's near the selenium orbitals, right? This band up there is sort of cadmium-like because it's near the cadmium functions. And these are sort of the wave functions of the entire crystal, but sometimes you get a surface atom that makes fewer connections, and so you get a state that falls within the gap. Okay, that's sort of conventional surface state kind of thinking. And these surface states provide another mechanism for recombination. So you can excite an electron, and the electron can rattle down using surface states instead of doing radiative recombination. Okay, and so there's a competition that gets set up. You excite a charge, and the charge can be quenched to this other mechanism instead of doing the radiative process, and that trapping then reduces the quantum yield. So the surfaces are like a huge part of the chemistry and photophysics of quantum dots, and surface ligands really strongly impact that. A very simple diagram here shows how an amine ligand can come in and bind a quantum dot. It would coordinate to an accepting orbital that's cadmium-like. And in so doing, you know, the Lewis acidic cadmium atom sort of lowers the lone pair of the amine. And the amine raises the empty orbital. And the result is you can push that empty orbital up into the band instead of within the gap. Okay, so now when you photoexcite, the electron no longer has this option of transferring to a mid-gap state because that orbital is now occupied by an amine ligand. So there are very few concrete descriptions of this kind of a relationship. This kind of a cartoon representation is sort of close to state of the art in terms of the thinking about this problem. Okay, it is the dark ages as far as I can tell. And things get a lot more complicated than this because these kinds of trapping processes can lead to charged quantum dots. And charged quantum dots have their own surface chemistry to think about. So that stuff is just not very well known. So, you know, I've been working in this area for quite a while now, and I thought I would just sort of talk about a number of issues here that are open, interesting questions. Simple things like what determines how strongly a ligand binds? You know, people haven't really studied that. It's quite difficult to study those kinds of issues. And quantum dots are actually ideal for that, these types of things, because you could use NMR spectroscopy to probe ligand binding to a surface. There's no equivalent method in traditional surface science, like solutions NMR of quantum dots. We haven't talked about this yet, but there are energies, the thermodynamic energies of forming a surface that are of a very significant importance to the reactivity of crystals and their growth. Okay, it's an issue that, or it's an energy people describe as a tension or a surface tension. And the thermodynamics of ligand binding, therefore, can impact that and change crystal growth kinetics. Another thing that is not very well understood, often described using very simplistic sphere kinds of representations. And then photoexcited charge recombination at surfaces, sometimes ligands prevent it, sometimes ligands cause it. That relationship is a total black box. Okay, so all these very simple things, the photophysics of recombination, the thermodynamics of forming a crystal, the strength of ligand binding to surfaces, that stuff is just not well understood at all. It is the Wild West as far as chemistry is concerned. So that's great. And you should be excited about these things, I think, because it's really sort of core aspects of chemistry. So the other thing is that coordination chemistry of ligands is very important to the application of quantum dots. So quantum dots are synthesized in organic solution. They have organic ligands. The organic ligands keep the particles apart from each other and make them soluble, so to speak, or dispersible. But they're also insulating. So you really can't get charge in and out when you have an organic ligand shell. And sometimes you want to put particles inside of a polymer, or you want to put them into water or something like that. And so making devices that pass current and putting particles into other media require that ligands can be exchanged, one ligand for another. And the exchange reactivity is something that has been studied using very empirical kinds of measurements. And that sort of reactivity is another area where there's lots of opportunities. Okay, so just a sort of historical perspective, the early syntheses, including the ones published by Munji Buendi that got Munji tenure, they were done in trioctylphosphine oxide. Okay, that was the solvent. And this is actually a product of Mike Steigerwald. So Mike Steigerwald, he used to use phosphine chalcogenides as ligands, as a source of chalcogen elements for various thin film making applications. And he was asked to make quantum dots. He brought these kinds of reagents to the field. Topo was or trioctylphosphine oxide was kind of one of the first things he reached for. And Munji actually was a postdoc there with Lewis. And it led to this idea, okay? Wonderful quantum dots were synthesized in cadselenide, and they had these phosphine oxide ligands, and you'd see pictures like this here. This really colored people's thinking in a way that was not explicitly talked about. The assumption here in this drawing that was widely accepted for a long time was that the ligands are neutral. And if you're an electron counter, the particles got to be neutral, okay? Because you're putting this thing in a bottle and it must be a charge neutral object overall. And that says something very specific about the quantum dot, okay? That sort of neutral ligand, neutral particle picture is one that computational people love. So you can put together density functional theory models of ligands binding particles, like there's your phosphine oxide ligand. Later, they found out, oh, you know what? It turns out that the main thing controlling the game in the synthesis of quantum dots and topo is actually an impurity, or a bunch of impurities, that are acids like phosphonic acid or phosphinic acid. And so they started looking at the binding of things like phosphonic acid, but this is a neutral phosphonic acid binding a neutral crystal. Okay, so that picture has really dominated the community that has thought about this stuff for many, many years, until I was a postdoc, basically. So I was one of the people that helped to kind of show that that picture is totally incomplete and really upside down. Later, people began looking at the stoichiometry of crystals, and they found actually that you end up with more metals than chalcogens in a sample of cadmium selenide. And that ratio of elements was size dependent. So again, if you're an electron counter and you say, all right, well, my crystal's got, say, 50% more lead than selenium in it, or sulfur here. And the smaller it gets, the amount of excess metal is going up and up and up. What does that say about the charge of the crystal? Well, it doesn't have to say anything unless you want it to be closed shell. If you think like a chemist, then you want octet, sort of octet obeying elements here. Then this is going to be lead 2 plus and selenium 2 minus. So you've got 50% extra lead 2 plus. That's not a neutral crystal. Okay, and so this realization, it took a little while to sink in, but it was throwing out the old picture, the neutral ligand and the neutral crystal. That was kind of the first crack in the armor. All right, so we're going to use pictures like these cartoons my group likes to draw to talk about this issue. So here's the old picture, and I've explicitly drawn cadmiums and seleniums or leads and seleniums or zincs and oxygens, whichever crystal it is, but it's a binary material. So I've drawn 2 atoms here, and you can think about this white circle in the middle as just being the perfect neutral crystal. And then I've explicitly included surface atoms to try and represent the empirical formula. So here there's an equal number of greens and reds. And so this is a neutral object. Here you have 6 greens and no reds, okay? And that's a charged object. So I'm not sure I said this very well on the previous slide, but the realization that the metal to chalcogen ratio increased as you went to smaller and smaller sizes was used to argue that the surfaces are metal enriched, okay? So, this basically follows a surface area to volume relationship. The smaller the particle, the higher the surface area, and therefore this metal enrichment must be a surface phenomenon. So if you have, let's say, a surface that's all metal enriched, and you want to charge neutral thing overall, then you have to have anions to balance the excess charge, right? That sort of makes perfect intuitive sense. But this was a totally, there are so many papers written about ligand binding and ligand exchange that totally missed the boat on this idea. And so really it turned out the ligands were not oleic acid molecules that were binding a neutral crystal, but that there was this charge balance interaction. So you can use the LXZ formalism, and I think everybody saw it. We did this in inorganic. So, there's your L-type ligands. There are the X-type ligands of interest. Again, carboxylate instead of carboxylic acid. All right, so this picture is the dominant one now. Everybody uses it. I think you know this. I'm not going to waste time except to say, right? X-type interactions. You donate 1 electron and you count using the neutral fragment picture. Z ligands contribute 0 electrons. They're acceptors. Okay, and then you can have this type of a situation where you have an L-type neutral donor and a Z-type neutral acceptor. All right, so it turns out things are slightly more complicated than what I mentioned before. We have this L-type neutral donor representation, and we have an X-type ligand here, where the X-type thing is balancing the charge of a metal-enriched quantum dot. But you can also have X-type ligands that have an outer sphere cation associated with them. So you can actually get ion pairs that bind. And then lastly, it turns out that the metal enrichment actually is something that's labile. So you can pull off metals along with their associated anions. And so you can think about these ligands as Z-type ligands, if you like. All right, so this picture, you know, really complicated things a lot, but it explains a lot of behavior, and it's a good way to think about these materials in general. I'm going to draw pictures like this, the subsequent slides. Really, of course, this is not a real representation of structure. It's a graphical way to represent empirical formula. You can think about, you know, the formula written up on top there as being similar to this kind of a representation. But I did my best. There should be no mistakes here. The number of green atoms in excess of red atoms is compensated by 2 anions in all of the surface chemical reactions I'll show you. Okay, so this thing is charge neutral. That empirical formula is balanced. All right, so we're going to talk about each of those classes and actually mostly our work on that, on the exchange. Oh, Jack is asking to come back in. Hang on a second here. There we go. All right, and the material system I'm going to tell you about is cadmium selenide balanced with carboxylate ligands and with metal enrichment. This is sort of a classic quantum dot material, and it's possible to make a lot of it. You can make 5 to 10 grams of this stuff in a 2-liter vessel. One of the ways you do so is by taking selenium dioxide and oxidizing the octadecene solvent with it. Actually reduce selenium dioxide to hydrogen selenide or something close to hydrogen selenide, but you make that thing into 2 minus in the presence of oleic acid and cadmium tetradecanoate. And you end up with this material here. You can purify it by precipitation. We'll talk about that stuff later, and then characterize it. And so my group, when I first got here and prior, but mostly after I arrived, would make this stuff, characterize the optical spectrum, and then also measure the NMR spectrum. And the NMR spectrum, what you'll see is mostly oleate ligands here. It's sort of broad, right? It's not very pretty if you're an organic chemist who likes small molecules, but the breadth is very, very valuable because it tells you that the ligands are bound. Okay, so here, for example, this is an internal standard that was added to do concentration measurements, and you can see the line width is very sharp compared to these peaks here. So the breadth is useful, as you'll see. You can use it as a proxy for saying its ligands are coordinated. So if you do this measurement and this measurement in a quantitative way on the same sample, you can determine the ratio of the semiconductor and the ligand in the material. That's a way to measure its empirical formula. Okay. And we express that ratio as actually a coverage. So we want to know how many ligands there are per particle, or really per nanometer squared, because we're looking at particles of different sizes. Okay, so sort of useful metric is what is the density? Okay. Particles can go from being 100 cadmium selenides to 1,000 cadmium selenides. Ligands from 20 or 50 to 300, right? So just telling you how many ligands is not helpful. That density of 3 carboxylates per nanometer squared is what's useful. All right, so the broadening in this spectrum is actually a consequence of differences in the degrees of solvation of the various ligands. So there's a number of mechanisms that can cause broadening. One is slow tumbling. Okay, big molecules don't tumble very quickly, and their spectra are more like solid-state NMR spectra. Solid-state NMR spectra have huge widths because the nucleus doesn't sample all possible orientations during the measurement. And when the molecule, the nucleus of interest is pointing this way relative to the field and this way relative to the field, it has a different chemical shift. So if the thing's tumbling very rapidly, you see one chemical shift. If it's moving very slowly, its chemical shift is changing during the measurement. If it's static, then you have a whole distribution of them. The slow tumbling is one of the mechanisms. Another is differences in the degree of solvation. So this particle is not a sphere, and not all ligands are the same. Some are on corners, edges, middle of facet, and they experience different degrees of solvation and give rise to heterogeneous broadening of the surface groups. You can see here the various signals in this ligand are numbered. As you move out into the solvent shell, like the methyl methyl group at the end of the chain, this peak is the sharpest. And as you go toward the crystal, the peaks become broader. And let's see, similar sorts of things here. In this case, however, you can see this chemical shift range is really only, well, I guess it's for all of the signals here. Yeah, there's A and F. You can see as you change what the solvent is, the spectrum changes very dramatically. Okay. In water, where these sorts of ethylene oxy chains, they like that medium, you know, they solvate well, they extend very nicely, and you get relatively sharp peaks, not too far away from the molecular signal. And something like toluene, the solvation is totally different, and you get this very broad signal. So the signal is very sensitive to the NMR solvent, and that's a sign that that solvation is really important. Okay, so one of the reactions that turns out to be probably the most important reaction, or one of the most important reactions for these kinds of things, is removal of cadmium carboxylate. Okay, and it turns out that this reaction is pretty fast, and it's reversible. So you can take a sample of cadmium selenide with oleate ligands on it, and add something like tetramethyl diamine to it and make this product, okay? And that move, which you will look at in a minute, can be studied with NMR spectroscopy, but it also can be studied with photoluminescence. So here's the photoluminescence quantum yield of many different samples where we've changed the coverage of carboxylate ligands. So you pull off some cadmium oleate, you isolate the material or you don't, and then you go back and measure its quantum yield, and you see this really strong dependence. It's very steep. And you can take the product after pulling off cadmium oleate and add it back, and the quantum yield goes back where it came from. So photoluminescence is a very strong function of ligand coverage. And this is a broadly, observed phenomenon. You reduce the ligand coverage, the photoluminescence quantum yield goes down. You increase the ligand coverage, and the quantum yield goes up. Now, it turns out that this change is actually a result of changing the number of on and off states. This is not just a difference in a competition between radiative and non-radiative trapping. It's that you make an off state, and then that particle in some charged form or whatever is no longer luminescent. So changing the ligand coverage impacts this Auger recombination business by creating a state that is no longer luminescent. And so one of the things that's been correlated with this relates to how cadmium oleate binds. So, the simplistic picture is that cadmium oleate comes in as a Lewis acid and it binds the surface selenium site. Right? And the surface selenium site is a lone pair sitting in the gap and a source of potential hole trapping. It turns out that the oleates also bind. And in fact, it seems they don't bind to the same atom. So while I draw this picture with two oleates on one cadmium, that's not the case. There's not enough room actually to do that type of thing in most cases. So the oleate will move on the crystal, okay? And it will bind another cadmium center. So that's not the whole story. It's not just selenium that's being bound. But what is observed is that hole trapping is less common when you put cadmium oleate on the surface. And there's been a study showing that that hole trapping actually arises from selenium orbital, selenium sites that are 2-coordinate. So 2-coordinate selenium creates a bad situation. And you can understand this with a sort of simplistic molecular orbital picture. Consider 2-coordinate selenium and 2-coordinate cadmium here. the valence band, top of the valence band in those surface states, they're going to be made of selenium 4p functions. And there are three different 4p functions. If you have a 2-coordinate selenium, there's one that binds to the adjacent cadmiums this way. There's another one this way, but that p orbital is orthogonal to the adjacent cadmiums. Okay, and it's that state that produces a very localized orbital that causes hole trapping. Okay, so if you form this type of a structure, as soon as you make it, you end up with this state here that falls within the gap. This is actually color-coded by the orbital contribution. Okay, so this is you can estimate the coefficient in front of each of the atomic functions that make up the linear combination this way. Pink is the selenium 4p. Okay, so this is mostly pure selenium 4p associated with that surface atom. So if you make 2-coordinate selenium, you end up with a localized p orbital, and that produces a state well within the band gap. And it gives rise to trapping. Something like 2-coordinate cadmium is not so terrible because it can bind to the adjacent seleniums. And actually, those states are mixed well into the band. Okay, so not all dangling bonds produce a surface state. That's one important conclusion. Those dangling bonds can mix with the orbitals of the crystal and produce wave functions that are delocalized. Really, it's when you have a highly localized thing that falls in the middle of the gap that you get a trap state like that. So that's one of the best correlations between surface structure and photoluminescence quantum yield that I'm aware of in quantum dots. So another thing that we did with this sort of study, which is going to be useful later, or I guess the way that we did, one of the ways that you can monitor this sort of thing is with NMR spectroscopy. And we really like oleate ligands for this. They're great because this peak here for the vinyl hydrogens is way away from everything else. And so it's straightforward to monitor this signal. And you can study the displacement of those oleates using these various molecules here. And you'll see down here at the bottom, very strong displacement reactivity up there. Not a lot has happened. And so with molecules like pyridine, for example, you see a signal corresponding to the bound ligands and then a signal corresponding to the free. They have different chemical shifts because their solvation is different. They have different breadths because of solvation differences and tumbling. So you can actually integrate these two signals and measure the extent of displacement. And there's really no other good way to do this in solids. People have looked at the binding of ligands to solid surfaces, but there's no equivalent measurement like this. It's very difficult to measure both the quantity of bound and free molecules in a titration or whatever. The one exception would be gas adsorption isotherms, but you have to make a lot of assumptions when interpreting those data. This is really pretty powerful and useful stuff. And, simple things like THF and alcohols, they're starting to cause the ligands to fall off. And then amines, all these various amines, turns out they have a really interesting impact on the extent of this reaction. I think probably the most surprising thing in here is the influence of the steric size of the amine on this displacement reaction. Take a look at tributylamine, for example. It really doesn't participate. It doesn't displace cadmium oleate very well at all. But if you take off 2 butyl groups and you just use a primary amine, the displacement is really very effective. These two amines have almost the same pKa. It turns out this one is more basic, which is not what chemists tend to think, but this one is slightly more basic than the tri-substituted one. But they're very, very close. Take 2 butyl groups and make them methyl groups, it's quite a bit more effective. Okay. So those differences are really very cool, I think. They say a lot. Another really interesting one is pyridine. Pyridine is a substantially weaker base than a trialkylamine or a primary amine or a phosphine, and yet it's very effective at displacing cadmium oleate. Okay. So this, I think, is also a steric effect. That's what we argued anyway, that this is a steric effect. Consider butyl dimethylamine and TMEDA, very similar binding groups, but now you have chelation, right? You can chelate and bind the crystal twice, so you can bind cadmium oleate twice. Turns out this stuff does not bind the crystal very well at all because of steric effects. Chelation does not meaningfully impact its coordination to the crystal. And the ring size difference here kind of speaks to that too. This is really about making a ring with cadmium oleate. 7-membered rings are not as favorable as 5-membered rings. All right, so these trends, you know, they say more than one thing. Some of it is like with the chelation, you know, there's the binding to the cadmium oleate in solution, but the steric effect that we were talking about suggests that it's binding to the crystal as well, right? So when you displace cadmium oleate, not only do you coordinate the cadmium that comes off, but you also bind the crystal. And so things like primary amines are great for this. Pyridine's pretty good for that, okay? And that's why pyridine is so high up on the list. And it's why things like tributylamine don't do this reaction very well. They're too bulky. So we're gonna, let's see here. I wanted to show, well, I'm gonna come back to that in just a second. Yeah, so let's talk about the L-type ligands for a second and the steric effect. One of the materials we're going to discuss is this material shown here. This is a ligand exchange reaction where we took a carboxylate terminated crystal and added chlorotrimethylsilane and trialkylphosphine to it. And the result is that you make this trimethylsilyl ester byproduct. And instead of oleate now on the crystal, you have chloride. So this is an X for X sort of an exchange, making the silicon oxygen bond in the product. You get a powder if you run that reaction, unless you add tributylphosphine, and then you get a solution, or you get a clear dispersion. And you know, the crystals are reasonably well separated from each other. You know, they're perfectly well dispersed, similar to the starting ones. Some really interesting changes to the absorption spectrum here. This peak is the lowest energy excitonic transition. It doesn't move around or anything because it's determined by the size of the crystal. But look at these other transitions. There's big differences in terms of how they responded to that change in ligand. And then the quantum yield drops. Anyway, those effects we have not totally sorted out on the optical spectrum, but they are related to coverage. I like this material because it has phosphorus in it. And phosphorus is a really wonderful nucleus for doing NMR spectroscopy. And we use this to do a bunch of titrations of the type shown here. So this example reaction just shows the primary amine coordinating the surface of the crystal. And you also you actually displace cadmium chloride from that crystal in the same reaction. Here's a signal for the phosphorus bonded to the crystal. That phosphine has a nice broad resonance. And as you add primary amine to this solution, you see the broad resonance go away. So we're going from 1/4 of an equivalent to 1 to 2 to 5 to 10 equivalents of primary amine. And as we do that, the bound signal from the phosphorus disappears. And then you end up at the end with a sharp signal for the free tributylphosphine. So it makes it possible to do this kind of ligand exchange monitoring directly, which is really quite powerful. I'm not going to get into the details of why the lines look like that, but I think there's some really interesting behavior going on in here that we really haven't totally sorted out yet, and I think is worth a lot more effort. So primary amines turn out to be better ligands than tributylphosphine, as we've shown in a couple of different ways, which you can learn from that titration experiment. So we've done this type of titration for a bunch of different molecules now to look at what ligands bind well. And this is a chart of binding affinity. And as you go to the right, binding affinity increases. Unless you're in this down here in this box, these molecules do not compete with tributylphosphine for the surface of the particle. These molecules do. And as you go to the right, they compete very effectively. As you go to the left, they don't compete much at all. So there's your tributylphosphine in the middle. That's our starting material. So that's kind of the relative point. And they've been ordered in a couple of ways. So let's just take a look at the amine column on the row of amines on the top. And you can see again the same phenomenon we saw in this cadmium oleate removal chemistry. As you go from primary amine to tertiary amine, the binding affinity of the amine goes way down, and the ligand is a much weaker competitor for the crystal. So that steric effect is very noticeable there. And the same is true in trialkyl phosphines. I really love this trend. Trimethylphosphine is a substantially better ligand than tributylphosphine. Okay, it's a meaningful difference. If you take two of the butyls and make them methyls, the coordinating power of the phosphine also goes way up. So here's a plot of some of these molecules on a graph showing the cone angle. You remember the cone angle is a measure of the steric size of the molecule. And then the pKa of the conjugate acid of the ligand. So this is like the ammonium ion pKa or the phosphonium ion pKa. So as you go to the right, the molecules become more basic, and as you go up, they become larger. So things down at the lower right of this chart really bind the best. Very basic molecules that have a small size. Things like an isocyanide, these are very weakly basic molecules. The pKa of a protonated isocyanide is very low. And so they look ideal to me in terms of the shape of the molecule. They're very sterically unencumbered, but they're not very good bases, so they don't coordinate well. Pyridine on the list again. Imidazole. Imidazole is more basic than pyridine, very small. It's a very effective ligand for a surface. All right, so why the strong steric effect, right? I mean, you have, organometallic people don't think of dimethyl and butylamine as being a lot bulkier than a primary amine. It is, but it's, this is a sort of very, very sensitive influence of sterics on coordination. And it turns out that the main thing it affects is actually the coverage of those molecules on the surface. All right, so you take these three. This drawing is, here's an example of me not balancing charge. These are all charge neutral crystals. And in fact, this study was done without cadmium chloride, I think. I've forgotten now. But if you look at the coverage of each of these molecules at saturation or whatever, it goes from 0.5 per nanometer squared for the trialkyl phosphine all the way up to greater than 3 per nanometer squared for the primary amine. So this is a very, very significant difference because, you're talking about a factor of 8 or something like that, is my estimate, for the number of ligands. So if you take a given quantum dot and you count those ligands, you'll find 8 times more if they're primary amines. Just switching to methyls, you get 4 times more. Okay. If these two molecules are competing with each other, the phosphorus is not really that different. So the bond dissociation energy of that metal phosphorus interaction is going to be the same, but you get 4 times more here. Okay, so you let these two molecules compete with each other, and the smaller one will outcompete the larger one. Primary amines seem to have a weaker bond dissociation energy than trialkyl phosphines do. But you can put 6 to 8 times more primary amines there. So the implication of this observation is that a small molecule may form a weaker bond to the crystal on a per ligand basis, but they fit. And so you can displace strongly coordinated stuff simply because you get to make more connections. A factor of 4 in bond dissociation energy is a really, really big difference in terms of, you know, I mean, what's an example? Yeah, bond association energy of CH bond is very high, right? 100 kcals per mole. 25 kcal per mole bond association energy is something that's falling apart at room temperature. Totally different. So anyway, this ligand packing thing, because of sterics, is a big deal. This is probably my favorite paper that the group has published. Don't tell former students. This is probably my favorite paper that the group has published. It was published in JACS, and it's not being cited very much. I mean, it is being cited, but it's not being cited very much. And my opinion is that this observation is hugely important to surface chemistry in general. You know, people want to design molecules to bind surfaces, but if the molecule is big, it's not going to work very well. It's almost boring. You know, it's like kind of ruins it. Size is really a big deal when considering ligand binding. All right. Well, I don't think I need to hammer this point home, but this very neatly explains why something like pyridine, which is not a very strong base, is very good at this displacement reaction. Pyridine is flat. Okay. It's very effective at this kind of ligand removal chemistry because you make many surface ligand interactions with it. All right. So let's talk one more aspect of coverage here. These sorts of materials, nobody really knows exactly what their surfaces look like. You know, it's a lot of hand waving. But if you take a zinc blend material of the type that we're working with here, it's a cubic crystal. And the two canonical surfaces that everybody talks about are the 111 and the 100. And here's a drawing of the particle roughly that we were working with, and the 100 surface and the 111. The 111 surface has 3 coordinated atoms, tri-coordinate atoms. That's at least the termination that has the lowest number of dangling bonds, and that surface actually has a single, if it made 4 connections, the 4th connection would be orthogonal to that facet, pointing straight up off of it. The 100 surface has got rows of atoms. Here's rows of atoms. And in this direction, actually, if each of these were cadmiums, then these atoms make 2 connections to the crystal. And they're missing 2 bonds. And the 2 bonds that are missing sort of point at each other. Okay. So these facets, very different coordination chemistry. They should have very different bond association energy with ligands, very different energies, etc. Okay. If you look at the density of these atoms on the crystal, it's the average density for the various facets I've considered is about 6 per nanometer squared. You know, but in a cubic crystal like this, half of the atoms on the surface will be selenium and half will be cadmium. So if you consider how many cadmium oleates you could bind to this crystal, it's going to be half the density of atoms. So instead of 6, it's something like 3 per nanometer squared. Excess cadmiums could coordinate to the surface. And so you might ask, well, where do they bind? And I think the 100 surface is the more significant one because it has 2 bonds missing. Those atoms are going to be much higher in energy. There's a lot more energy to be gained. You make 2 connections to the cadmium that associates with that facet. Okay, so it seems that 100 is where things bind tightly. 111 is where things will bind more weakly. There are also edges. There are other facets. There's the 110 facet. You know, and all of that stuff is going to impact bond association energy and affinity. Another very significant consequence of this actually relates to the sterics. So here's a bunch of materials, diamond, zinc, and indium. And each one of these facets I've plotted, or sorry, these materials, I plotted the surface atom densities for the 111 and 100 crystal surfaces. Look at diamond, gets all the way up to 18 per nanometer squared. That's a very, very dense surface. And then this dashed green line here is the packing density of crystalline alkanes. And so if you have n alkanes all packed side by side, you can get to a density of about 4.9 per nanometer squared. That's a crystal of alkanes. All of these facets have surface atom densities that are higher than that, with a few exceptions. There's a mismatch there, right? If you want to put ligands down on surfaces, the ligands are too big, particularly if you're diamond. Hydrogen is too big if you're diamond. Okay, so how do you passivate or bind ligands to the surfaces of a diamond crystal? You have to do reconstruction in the case of diamond. Even silicon has significant problems with that. So you can see, steric effects are a big deal in material science, in surface chemistry. They're a really big deal. They dictate all kinds of properties, and it's not something that's on people's radar. You don't hear people talking about this type of thing when you are thinking about molecules interacting with inorganic solids. This is sort of, it's a big deal. All right. So enough of that. Go cite my paper. So, okay. So I want to talk a little bit about stabilization of dispersions. And a lot of these organic chains, they sort of hang off the surface and they help keep the particles apart from each other. And so when particle chemists talk about sterics, they tend to talk about the length of the molecule, not its sort of radial steric size. So simple things like amines and phosphines and thiols, L-type ligands, they come in, they bring their chain with them, or you can have a metal carboxylate come in and absorb, and that gives you a particle that's soluble in hydrocarbon media. You can also have situations where you have a metal cation and some outer sphere anion, or you have an inner sphere anion and an outer sphere cation creating a salt, this like charged object. And in polar media, those charges will dissociate and you dissolve just like you dissolve sodium chloride. Okay. And people talk about that as being electrostatic stabilization. And then there's also this type of a situation where you have an anion that's binding and the outer sphere cation is actually organic and has a big long chain on it. And this thing dissolves in both, but you can dissolve things like this in toluene or maybe not hexane, but you can dissolve it in chloroform and that type of thing. Okay, so there's sort of these types of situations in colloid chemistry, and it's often the case that ligand environments are so complicated that you get a mixture of all of them. Okay, and you're stuck trying to parse what is what, how much of each is there. So let's talk for a minute about this electrostatic stabilization. Okay, here's a depiction of what's going on in solution when you have electrostatically stabilized colloids. You have essentially a salt that's adsorbed to that crystal. There's a binding constant for that salt. And then there's a charge separation that happens. Okay, and you end up with two particles here in this example that have a net negative charge with inside of that green ring. And the result is that those two particles do not want to associate with each other. There's an electrostatic repulsion that happens because they have the same charge. So there's this thing called DLVO theory, which describes that type of thing. And it considers the electric double layer that forms. And then it also considers something called the slipping plane. So the stern layer is this green ring here that defines the net charge of the particle, but there's something else called the slipping plane. The slipping plane is actually it's a measure of which anions are actually moving with the particle. Okay, so there's a measurement called light scattering. You put your sample in front of a laser. When a particle is in front of the beam, it scatters light. You can measure that motion and determine how big particles are. And the size of the particle is not just the little inorganic bit, it's also any associated cations that fall within this dashed blue circle. Okay, so if you measure how big the particle is in terms of how fast it diffuses, you have to consider the associated cations within that blue circle, and that blue circle then is referred to as the slipping plane. All right, so here's the surface potential, which is just a measure of the charge density as you move away from the surface. All of this stuff falls within what they call the electric double layer, and you can see it falls off pretty quickly. So, right, electric potential reaches 0 at the boundary of the electric double layer. That's what defines it. But you also have to consider the slipping plane, shear plane thing, which tells you about diffusivity. Oh, and the last definition there is the zeta potential. Okay, so there's this, you'll hear people talk about zeta potentials when they talk about charged particles. Zeta potential is a measure of the electric potential at the slipping plane. It's something that you measure with light scattering. All right, so DLVO theory analyzes this, the electrostatic repulsion here. There are the names, I don't know how to pronounce them. Dairy again, Landau, Buoy, and Overbeek. This is the potential of two particles, and it's defined by the van der Waals force, which is an attractive energy for spheres, and the electric repulsive potential, which is related to this charging that I mentioned. So the van der Waals attraction goes as the radius. Okay, so the bigger the particle, the stronger the interaction, the stronger the van der Waals attraction. There's something called a Hamaker constant, which is related to polarizability. Things that are very polarizable have much larger van der Waals attractive force. And then there's the distance between the two particles. Okay, so the van der Waals attractive potential goes up as 1 over that distance. You can see it plotted here. There's the 1 over the distance. You go closer and closer and closer, and the attraction gets stronger and stronger and stronger. Electrostatic repulsion goes as the exponent of 1 over that distance. Okay, and so it's sort of this line here. You have to consider the dielectric constant of the medium, and you have to consider the zeta potential of the particle. And zeta potential squared. So the most important issue in defining this electrostatic repulsive energy relates to how charged that particle surface is. Okay, it's more important than the size of the particle and that type of thing. Okay, so those two things compete with each other, and the actual attractive potential looks something like this. There's sort of a preferred distance where things are relatively stable, but getting them any closer, it is counteracted by that electrostatic repulsion. So let me just say that this is a very common thing in chemistry. We don't really learn about this sort of thing, but people who do cross-coupling catalysis, for example, are often working with electrostatically stabilized metal particles, and they don't know it. You do some organic synthetic reaction, you produce a metal salt as a byproduct. It's supposed to precipitate as a powder, and you filter it away. And formation of these types of electrostatically stabilized dispersions gives rise to impurities in your sample. All kinds of colloids are stabilized this way. Okay, so this is a really big deal. A lot of people have thought about it. As relates to the stability, you can sort of, as I said, the zeta potential is probably the most important thing for these sorts of materials, and you can quantify relative stabilities based on the magnitude of that zeta potential. So as I mentioned, this is studied with light scattering, and people say that like greater than 30 is where you want to be. All right, so one more aside there. There's a sample of gold colloids. Gold colloids are often stabilized in this manner. There's a sample of them made in like the 1700s or 1800s that's sitting in a museum someplace, and you can still see these particles are stabilized in the solution by this electrostatic means. Okay, so this stuff, this is not just a toy, it really works. Okay, I don't think I'm going to spend a lot of time talking about that. Okay, all right, so we'll spend a few more minutes talking about ion pairing interactions if my computer doesn't die. Uh, 1%. Well, I think class is over for today. I guess I can try and plug it in. I think I have here. Well, I think I'll just stop and pick this up next time. Okay. Does anybody have any questions?